Hey everyone, we're going to get started today on 5.2, which is going to be concepts review on the mean value theorem and Rolle's theorem. So why don't we just go ahead and get started on that. Okay, so for what we're seeing here, you've got Rolle's theorem stating that if a function is continuous at every point in a closed interval and differentiable on every point on the interior, then there's at least one number where the derivative is equal to 0. Okay, and I think I forgot to read that f of a has to equal f of b. Okay, and that kind of makes sense. This is actually, the way I look at it is it's an extension of the mean value theorem, or maybe the mean value theorem is an extension of this. I'm not quite sure which. But the one which you may not be thinking about is this variation of the Rolle's theorem, which says that if the function is continuous at every point in the closed interval, then there has to be a critical point. Okay? So if f of a equals f of b, which means we have a horizontal secant line that connects a and b, then there has to be a critical point between a and b. So, looking at letter A, does this qualify for this variation? Is f of a equal f of b? Well, I think it is. Looking over here, f of a and f of b, they are the same height vertically speaking. So, yeah, their Rolle's theorem applies. Let's find the critical point, and it is right here. That's the place where the derivative doesn't exist. Letter B. Is this function continuous everywhere between a and b? And I believe it is. Next, does f of a equal f of b? And I believe it does. Taking a look here, f of a is here. F of b is here. Those two lie at the same vertical height. So that would mean that we should be able to find some critical points. Here's a critical point, has a horizontal tangent line. Here's another critical point, again, horizontal tangent line. Letter C, does this qualify? Continuous? Yes. F of a equals f of b? Yes. Critical points, places where the derivative is equal to 0, or where the derivative is undefined. So those are those places right here. And then, probably just to mess with you. Letter D, you have f of a being way down over here, and f of b being way up over here. And since f of a is not equal to f of b, the Rolle's theorem doesn't apply, which means the variation on Rolle's theorem doesn't apply as well. That brings us to the mean value theorem, and the mean value theorem is kind of like Rolle's theorem, but the major exception here is that when you do the mean value theorem, you're looking for not tangent lines, but places where the tangent line is parallel to the secant line drawn. So if I take a look at letter A, we have a place where the function is continuous at every point between a and b, continuous and differentiable. So let's take a look at what that secant line looks like. There's the secant line. It connects a and b. And then are there any places where the tangent line is parallel to the secant line? Well, I think I've identified two of them, right there and right there. Okay, this could have very well have been said using Rolle's theorem, but the fact that we're using the mean value theorem just kind of highlights to you that the mean value theorem and Rolle's theorem are kind of the same idea. Taking a look at letter B, f of a is not equal to f of b. Just f of a is down here, f of b is up here. Those are not the same, so Rolle's theorem doesn't apply. The mean value theorem also doesn't apply because right here we have a place that is not differentiable. The slope from the left and the slope from the right do not match. So look, this function is not differentiable, so the mean value theorem doesn't apply. Letter C, kind of the same thing. This is continuous again, but right here we have a vertical tangent line. And vertical tangent line tells me that the mean value, or the derivative, doesn't exist, so the mean value theorem shouldn't apply as well. Okay, letter D. Now, we have a function that is definitely continuous, and it's a line, like line by linear line. So that means that the slope is everywhere is the same. So the slope of the secant line that is connecting A and B, that's this line right here. Is there any place that has that same slope? Well, actually every place between A and B has that same slope. So every point between A and B is a C for the mean value theorem. Letter E, again, continuous. Not differentiable right over here. So that tells me that the mean value theorem shouldn't apply as well. So those are all of our cases for question 2, I believe. And that moves us to the next section here, where we've got suppose f is a function with a continuous first and second derivative. That means that the mean value theorem should apply. Well, no, they're not necessarily differentiable, so the mean value theorem doesn't necessarily apply. But that variation of Rolle's theorem might apply. No, it doesn't as well. Whose values for f and f prime at the points 0 and 4 are given below. So letter A, prove that there exists a value C between 0 and 4 such that f prime of C equals 1/2. And as I'm reading that one, that sounds a lot like the setup for a mean value theorem. So you should kind of train yourself to recognize the way that that's being said. We're trying to prove that the derivative is equal to a number, and that number isn't 0. We're given a continuous function. So that means that we should be able to use mean value theorem. Okay, so not even knowing if it applies, I would start computing the slope of the secant line between 0 and 4, because that's what the mean value theorem would work on. So the mean value theorem does apply. So for some number between 0 and 4, the derivative of that number has to equal f of 4 minus f of 0 over 4 minus 0. And when you look at that equation, that's just the slope equation. Mean value theorem is just saying the slope has to equal the derivative someplace in the interval. You simplify that, you get 1/2, and there you go. You've proven exactly what you were supposed to show. Letter B is kind of the same thing, only we're showing that f double prime of D is equal to -1. And if f double prime is a derivative of f prime, that means that we should be able to use the mean value theorem on f prime, by the way. So does the mean value theorem apply for f prime? Is the graph of f prime continuous and differentiable? And I think that was part of the setup. So even without knowing what you're doing, I would start trying to figure out the slope of the secant line of f prime. So here we have the mean value theorem applies for f prime, because for some point, we're calling that D, between 0 and 4, the slope of the secant line, f prime of 4 minus f prime of 0 over 4 minus 0, has to equal -1. And as you can see, like you've predicted, that slope is going to be -1. So that's it here for section, what was this, 5.2. I really should check. Yeah, that's 5.2. All right, section 5.2, and I'll see you next time when we do more calculus review.